Good to get started? Sure, cool. So, hi everyone, I'm Xurong Liang, a PhD student from the University of Queensland, Australia. So my research topic mainly focuses on library recommender systems, and today I'm glad to have the opportunity to share with you my latest work, which is library embeddings for graph collaborative filtering. So in the upcoming slides, first I'm going to give you a little bit of background about why the memory efficiency of the recommender system matters and analyze the drawbacks of the, the current optimization work. And then I'll introduce the motivation and the structure of our work and demonstrate why our work works out from its competitors in achieving a balanced trade-off between memory efficiency and recommendation performance. So recommender systems has been widely deployed in various businesses such as e-commerce industries. Today, the graph-based recommender systems, which leverage the graph neural networks for collaborative signal propagation, have attracted vast interest from both academia and industry due to their strong capabilities in modeling user-identity interaction and embedding learning. Despite their good recommendation accuracies, GNN-based recommender systems cannot avoid the memory efficiency problem due to a full embedding table is commonly adopted, wherein each user identity is assigned a physically unique embedding vector, which means amid the sheer volume of users and items in e-commerce applications, the embedding table inevitably becomes the heaviest part of the entire recommender system. So as you can see down here, we've got this figure, right? You can see that as the number of embedding vectors increases rapidly in large-scale deployment, it actually makes it hard to fit the state-of-the-art GNN-based recommender systems in devices with limited hardware specifications. So to this end, optimizing the memory consumption of the embedding table becomes the primary solution for a library embedding for a library recommender system. So reviewing on-the-shelf embedding optimization strategies, we can roughly divide them into two categories. The first one focuses on AutoML, in which the automatic machine learning algorithm is devised to learn a proper dimension size for each entity from a predefined candidate size search space. Nevertheless, these methods often suffered from the slow training speed due to the inherited drawback of neural architecture search, and say that if you're using a reinforcement learning technique, you will also incur enormously large search space. For all these reasons, it actually makes it like this type of method not really realistically suitable for large-scale deployment. And there is also a subset of AutoML-based methods that conduct automatic pruning to identify the redundant elements in the embedding table and remove them to a safe space. However, the pruning procedure is often conducted on the full embedding table directly. In a case where the memory budget is tight, it is possible that the usable dimension size for each entity shrink dramatically, even resulting with embeddings with no valid elements at all. So for this instance, the recommendation accuracy will be greatly compromised as well. The second type of embedding optimization strategy is parameter sharing, wherein a meta-embedding codebooks, which contains far fewer entries than the full embedding table, is introduced. A suitable meta-embedding assignment scheme, such as a set of hash functions, is defined so that, let's say, given a set of entity embedding, a sequence of hash indexes can then be calculated using the set of retrieved meta-embeddings for the current entity. And then the entity embedding can be formed by performing a compositional operation on the set of retrieved meta-embeddings. For this reason, these methods are also known as the compositional embedding methods. Although most compositional embedding methods are indeed capable of generating dense real-value entity embeddings, a major concern is that these methods often assign meta-embeddings based on the hash functions, which in turn makes the meta-embeddings assignment a predefined and fixed decision. We argue that such a fixed assignment scheme retains minimal semantic associations between entities. The reason is that the meta-embeddings assigned to each entity are solely determined by the user item IDs, which are actually mutually independent. Whereas the interaction information that is concealed naturally in the user item interaction graph is now completely set aside. That said, it is possible for entities that are not similar in reality to receive a highly similar composed entity embedding. In this case, the entity affinity is not properly represented in their embeddings. In addition, most compositional embedding methods allocate a unanimous weight to all meta-embeddings with no mechanisms to differentiate their contributions in an entity's compositional embedding. As a result, the embedding expressiveness and recommendation performance can be heavily affected. This impact may even be worse in GNN-based collaborative filtering, where the user item links are explicitly counted for message passing. So to this end, we designed a method called LeGraph, which is the shorthand for lightweight embeddings for graph collaborative filtering, to solve the problem by devising graph propagation between entities and meta-embeddings. The method features a flexible compositional embedding scheme by introducing a learnable real-value assignment matrix to replace the handcrafted hash functions. So in LeGraph, we adopt a single meta codebook E-meta with dimension of C times D, where C here is the number of meta-embeddings utilized in the framework, and D here is the dimension size of each meta-embedding. We also introduce a learnable assignment matrix called S of the shape N times C, where N here is the total number of users and items. Especially, each row of the assignment matrix S corresponds to a user item entity, where the non-zero element indicates which meta-embeddings are selected out of the C choices and their weight in the composition of the entity embedding. In this way, we can now replace this full embedding table by simply performing a matrix multiplication between S and E-meta. It is worth noting that considering the size of a dense assignment matrix S, we actually regulate this assignment matrix to be highly sparse. Detailed instructions on updating S are deferred to later sites. And since LeGraph deploys a dense meta codebook and a highly sparse assignment matrix, the space complexity is going to be O of Tn plus Cd, where T here is the number of non-zero elements per row in the assignment matrix. In our setting, we shall have C to be much smaller than N, and T is also much smaller than C. Our algorithm utilizes much lower memory consumption than the full embedding table, which exerts a space complexity of O of ND. In LeGraph, since the full embedding table E hat is derived from the meta codebook E-meta, each meta embedding is essentially linked to a list of nodes. We now enable the graph propagation between the entities and meta embeddings by constructing an expanded interaction graph called A prime, which incorporates the assignment matrix into the user item interaction matrix A. That means by using the merged interaction graph, the collaborative signal can now flow between both entities and the meta embeddings they are composed from, as well as the entities they have interaction with. We stack E hat and E meta into a big matrix for simultaneous propagation. The propagated full embedding table H full and the meta embedding codebook H meta can then be drawn from the graph propagated stacked output. So to update the learnable assignment matrix S, we propose a gradient-free update strategy. This is why one can directly update S via gradient descent. We argue that updating S and E meta at the same time through backpropagation may introduce difficulties in finding stable solution due to their co-adaptation. Another side benefit of gradient-free update is that the in-place modification on S now becomes possible so that we can sparsify it on the fly. Recall that the entity embeddings are gathered from the matrix multiplication between the assignment matrix S and the meta codebook E meta, which means that the element in each row of S indicates the similarity score between a nominated entity and all meta embeddings. Optimally, if such a similarity holds in the input layer, it should also hold between the entity embeddings and the meta embeddings after L layers of propagation. So to visualize this idea, we can take a look at this figure at the top. Let's say using entity 1 as example. So if H full and H meta are in optimal form, then the two vectors in the hidden space should be as close as possible. This requires the assignment matrix S to reflect the relationship between H full and H meta accurately. So to do this, we update S by taking the matrix modification of H full and the inverse of H meta. However, the direct inverse of H meta does not always exist, since H meta commonly is not a square matrix. As a wraparound, we approximate the inverse with the pseudo-inverse by resorting it to the more Penrose pseudo-inverse and solve the pseudo-inverse of H meta through a singular value decomposition. We put forward the pseudocode algorithm on this slide. Lie graph essentially contains two stages. The first stage is the warm-up training stage, wherein the meta codebook is updated while freezing the assignment matrix to provide learning stability. Once the learning of the meta codebook converges, we alternatively update between the learnable assignment matrix and the meta codebook to refine and decompose embeddings. We evaluated the performance of Lie graph on Goala, Yelp 2020, and Amazon book datasets. For evaluation metrics, we pick NDCG at 10 and record at 10, which are common metrics used in personalized recommendation settings. For baselines, we include AutoML-based ESAPN, AutoIn, PEP, OptImbed, and SIS. Compositional-based QR, DHE, and Nimble TT. We adopt Light GCN as the base recommender for baselines and Lie graph. To showcase Lie graph's performance and memory efficiency trade-off, we also displayed the result of unified dimensionality settings evaluated on large dimension sizes, which are 64 and 128 in our case. For hyperparameter settings, we set the dimension size of meta embeddings to 128 and adopt a meta codebook bucket size of 500. We show the performance of baselines evaluated under similar parameter sizes obtained by Lie graph, or the lowest parameter size they can reach. Detailed settings about other hyperparameters can be found in our paper. The results are reviewed in this chart here. We display the magnitude of parameter sizes directly to give a more intuitive comparison of memory efficiency of methods. The best results are highlighted in red, and then the second best ones are highlighted in green. We can see that Lie graph actually yields the best performance across both evaluation metrics consistently on all three datasets. The values evaluated using both NDCG at 10 and record at 10 on Lie graph actually forms a great gap between the second best baseline, SIS, and AutoImb. This means that our newly proposed method, Lie graph, is indeed superior to all baselines in terms of retaining embedding quality amid a tiny memory budget. Now let's compare the result of Lie graph with the UD settings. So using Goala dataset as an example, Lie graph causes a 6.5% drop in performance, but the parameter size obtained by Lie graph is actually 22 times smaller than the UD settings with a dimension of 64 and 44 times smaller than that with a dimension of 128. This shows an optimal trade-off between recommendation performance and memory usage, as the recommendation is barely affected by the memory-efficient embedding layer. We conducted more experiments to verify the effectiveness of Lie graph. Interested audiences can refer to our paper for details. And yeah, that is the end of my presentation. Thanks for listening. Any questions are welcome.